Let me remind you that if we have a matrix n by m, then this matrix defines a transformation from, let's say, Cm into Cn given by V into AB. Remember, this is an n by m matrix, and this vector is an m by 1 vector. Then we end up with a n by 1 vector, which is an element here in Cn. As an example, we have A equal to 1, negative 1, 3, 1, 0. Then, in this case, T of A of x, y, z is just 2, 1, negative 1, 3, 1, 0 times x, y, z, and this is 2x plus y minus c, 3x plus y. If we have the transformation like this, like t of x, let's say x, y, z equal to 5x minus y, 3x plus y plus c, and we wonder where this transformation comes from. What is the matrix that produces this transformation? Let's suppose that this is a T of B. We have pointed out that the way to do it is just to compute T of the vector E1. T of the vector E1 is T of 1, 0, 0, which is 5, 3. And this vector produces the first column of B. And we have 5, 3. T of E2 is T of 0, 1, 0. And this is x equal 0, y equal 1, z equal 0. Then we get negative 1, 1. And this is the second column of B. And T of E3, which is T of 0, 0, 1. And in this case, x is 0, y is 0, and z is 1. And then you get, when you replace here, you get 0, 1. That means 0, 1. This means that this transformation is just the transformation T of B with this choice of B. If we think about what we have done, we realize that essentially what we are doing is computing the matrix representation of this transformation with respect to the bases E1, E2, and E3 in the domain, and E1 and E2 in the codomain. Then the matrices that we have defined before as T of A, they are just the matrix representation of the transformations given in this way when we use the canonical basis. Let's suppose that we have a square matrix n by n, and then this matrix defines a transformation from Cn to Cn. And then let's suppose that this transformation is injective and surjective. And therefore it has an inverse, and we want to compute the inverse. Then this is the situation. Here we have Cn, and the domain is Cn, the codomain is Cn, and here is the transformation T of A that is produced by this non-singular matrix A. Then the transformation T of A goes in this direction, and the transformation, the inverse goes in this direction. But then if we want to compute the first column of A inverse, then we need to find out the output of T inverse of A of the vector E1. But that output is an input here such that the original transformation sends this input into E1. And then essentially to compute this number, this vector, which is the first column of A inverse, we have to solve this system, AX equal to E1. Then we have to write down the matrix, A11, A1n, AN1, ANN, and here we write 1, 0, 0. And then we need to do row reduction, and we are completely sure that here in this n by n block, we're going to get the identity because we are assuming that this transformation is injected as surjective. That means that this matrix is non-singular. And whatever we get here, this is going to be the first column of the matrix A inverse. We can solve simultaneously all the columns. Essentially, to compute the second column, we need to find an element here in the domain that goes to E2. And to solve it, we could say, I'm going to solve the system with augmented matrix equal to this matrix, 0, 1, 0, 0. But we can't do this simultaneously and just do row reduction to this matrix, A11, A1n, AN1, ANN. Here we write 0, 1, 0, 0, 0, 1, 0. And if we do the same argument, we realize that we can find all the columns of A inverse just by doing row reduction to this matrix, like this. And then essentially the procedure that we need to do to compute the inverse of a matrix is we need to create a matrix of dimension n by 2n, which is just the matrix A that you want to compute the inverse, and then add to the right the identity matrix, and then we do row reduction, and then this matrix A is going to, when we do row reduction, this is going to become the identity if this is the reduced echelon form of this n by 2n matrix. And then the matrix that entered here in this last block n by n, that matrix is the inverse of B. Then B is just A inverse. Let's do an example that illustrates this argument. For example, if we want to compute the inverse of this matrix, then we need to consider the matrix 1, 3, 2, 3, 2, 1, negative 3, 1, 1, and then we add the identity on the right of that matrix. And then we find the reduced echelon form of this matrix, which is the matrix 1, 0, 0, 0, 1, 0, 0, 0, 1, 1, negative 1, negative 1, negative 6, 7, 5, 9, negative 10, negative 7. The inverse of A is the matrix 1, negative 1, negative 1, negative 6, 7, 5, 9, negative 10, negative 7. Let's do a very easy example. Let's suppose that A is the matrix 1, 1, negative 1, 2. Then we can use the formula A inverse equals to 1 over AD minus BC, D minus B minus CA. This is the formula for the inverse of the matrix A equal A, B, C, D. To compute the inverse, you divide by the determinant, and then you flip these two elements, and you change the sign of these two elements here. And as you can see, this works only if the determinant is different from 0, because you are dividing by that determinant. Then if I use that formula, I get that A inverse is just 1 over the determinant. The determinant would be 2 minus negative 1 is 3. And then I change this 2 to 1, and I change the sign of this. Then I get the matrix 2/3, negative 1/3, 1/3, and 1/3. Now let's try to do this by using row reduction. If we start here, 1, 1, negative 1, 2, and we add the identity, then this is row equivalent. Let's do row 1 plus row 2, and let's add this to row 2. Let's change row 2 by adding row 1, and I get 1, 1, 1, 0, 0, 3, 1, 1. Then I can divide row 3 by 1/3, by 3, sorry. And then I get 1, 1, 1, 0, 0, 1, 1/3, 1/3. And then I can change row 1 by adding to it a negative row 2. And then I will get 0, 1, 1/3, 1/3. And I'm going to add negative this, then is 1 minus 0 is 1, 1 minus 1 is 0, 1 minus 1/3 is 2/3, and 0 minus 1/3 is negative 1/3. That means that A inverse, using this procedure that I have explained using transformations, is just the matrix 2/3, negative 1/3, 1/3, and 1/3, which agrees with this answer. For 2 by 2 matrices, I believe this is the most efficient way to find the inverse, but in general for 3 by 3, 4 by 4, this method of adding the identity to the right and doing row reduction so that you can find the reduced echelon form is the most efficient. Let's do one last example. If this is our matrix A, then to compute the inverse, we need to find the reduced echelon form of the following matrix: 1, 5, 2, 4, 3, 3, 1, 0, negative 3, 1, 1, 3, 2, 2, 0, 1, and then we add the identity here. This time I'm going to use the computer to find the reduced echelon form of this matrix, and you will see that this is 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. And here you get the matrix -2, -7 fourth, -9 fourth, -5 fourth, -3, 11 fourth, 13 fourth, 9 fourth, 3, -2, -3, and -3, and 2, -2, -2, and -1. That means that A inverse is the matrix 2, -7 fourth, -9 fourth, -5 fourth, -3, 11 fourth, 13 fourth, 9 fourth, 3, -2, -3, -3, 2, -2, -2, and -1.